Hi everyone, my name is Alex. I'm an engineer and my passion is with design, development and prototype production of all sorts of engineering solutions. In this video I'd like to show you how I managed to machine the sidewalls of a new bending press design or a press brake design that I'm currently working on. And the interesting thing about these sidewalls is that they're way too large and too heavy for my machining equipment. So let's take a look. First of all, beware that this video does not show a very economical way to machine large and heavy parts on small machines. It is rather intended to show what can be done on your own with limited equipment. This job was a clear case of minimizing costs without taking into account my own labor. That is, minimizing financial risk. Well, the parts are about 2 meters tall. They're about 800 millimeters wide. 13 millimeters thick. They are made out of medium strength carbon steel and weigh about 180 kilograms, which is about 360 pounds each. Here is one of the plasma cut blanks. I had the blanks cut by a company in Upper Austria who did a perfect job. Just look at the quality of the cut faces. There is almost no scaling. All the blanks have but very little distortion. With this type of steel, the cut faces are hardened due to the plasma cutting process about short of a millimeter deep. At the edges a bit more than a millimeter. So the first step was to radius all the edges, first of all for the burring, and secondly to get rid of some of the hardened material. First I put on a 45-degree chamfer on all edges with the angle grinder and the roughing disc. Then I chamfered the two new edges again to get close to a 2 millimeter radius. I'd love to tell you that this was actual working speed, as Robin Dransetti said in one of his videos, but frankly this is sped up. I should have tried to round over the edges with the aid of a router with a carbide insert, as Tom Lipton showed a while ago on his etching press hand wheels. But unfortunately I was pressed for time and had no router at hand, so the angle grinder it was. Then I rounded over the 3 chamfers with a flap disc. Changing to a newer flap disc, which is not so consumed and reaches the tight inside radii. Finally, finishing the tight inside radii and the cut faces with the straight grinder and the stone, as well as a flap wheel. Not shown in the video is cleaning the sheet's faces from spatter with the aid of a stone. I like the burring so much. The time lapse shows me doing one side, but as you can imagine, I had to repeat this 3 times more to cover both sides on both blanks. For indicating these large parts, I had to make an extension for the indicator base. It attaches to the quill housing with a 3-point bearing, one of the 3 points being a bronze bolt. On my WF-1 mill, the table moves as you traverse the X and Z axis. This makes the job at hand a little difficult, because the heavy blanks must move with the table. So just hanging the blank from the crane while doing the machining is out of the question, because you'd constantly have to work the crane to ensure a proper amount of lift on the blank. Instead, I decided to use a counterweight to compensate for the weight of the blank while it's being worked by the mill. For this, I needed a pulley block that accepts standard 1-ton hoisting slings. On the market, I could only find pulley blocks for wire rope, so I had to make my own. It's a very simple design with an aluminum pulley, 2 ball bearings and a welded fork. It's all made from leftover material, however I had to buy the ball bearings. For the counterweight I could borrow 20 pieces of 10 kg weights from work, but I had to make a holder for these to attach them to the hoisting sling. Basically it is a 12 mm rod with a plate at the bottom. We start with these 2 M12 threaded holes for the feet. This is the setup of the counterweight. Important here is to make sure that the sling cannot slide away from the center of gravity of the blank. With some setups, my dad managed to find the time to give me a hand. Thanks, Dad. By using a counterweight, the crane must take twice the blank's weight. In the case at hand, this is 360 kilograms. The crane I used is my dad's engine crane, for which he gave me the permission to consume it. But surprisingly, and even though I wasn't gentle to it, it held up all the way with no problems whatsoever. Here I used 2 prisms to get the blank off of the table, high enough for the horizontal spindle. With the counterweight, you always have to make sure that it can move freely without hooking onto the part. Then it could become dangerous. Finding the edges. Tapping takes so long here because the wrench hits the table and has to be reset constantly. And checking the fit of the rubber foot. Next we'll machine these two faces. These two faces have a 4 bolt hole pattern each. Down here frame 16 bolts and up here frame 8 bolts. We have to do the faces in 2 setups because they're too far apart and they should be parallel with each other, so we have to indicate those 2 setups. And they should be parallel with the back edge of the blank here, so we have to indicate this, that one as well. For this operation the setup is without the table but with the prisms on the vertical clamping face to clear the DRO's glass scale. Here I am clamping a straight edge to the blank as a reference for indicating and for checking dimensions. Here the blank is standing free. I had to be very careful to keep it from tipping over. Now safe again, hanging on the crane. Here I'm using the extension for indicating along the straight edge, which is clamped onto the blank as a reference. The adjustability of the extension is a handy feature here. The indicator is hard to see here, but this picture gives a better view of the indicating process on the other blank, where I machined the 2 faces vice versa. This is digging through the hardened crust for plasma cutting with the carbide face mill and machining to dimension. This is finding the blank center and drilling and tapping the M8 bolt hole pattern. Again, sadly, this is not actual working speed. I'm always having one eye on the counterweight to make sure it doesn't hook onto the blank or touch the ground. This is very important because otherwise the blank's full weight would have to be carried by the mill, which would probably break out the T-nuts from the table and set me back a few thousand euros. Next is changing setup for machining the second phase. To turn the part, I had to get the counterweight out of the way. And that's why it's called pumping iron.
Pumping iron.
This setup I indicated along the already machined face. Here a picture from doing it vice versa on the other part. This is again digging through the hardened crust from plasma cutting. And here I'm checking dimension in relation to the straight edge. Doing this with a good tape measure should give me a tolerance of about 0.2 of a millimeter, which is alright in this case. And here drilled and tapped with M16. Next we drill these two through holes. They just hold threaded fasteners for a spacing plate. Don't need to be precise, so we place them on a scribe line. This is the machine setup for drilling. I used my universal clamping block to get the blank further away from the spindle to give enough room for the drill. My dad gave me a hand here again with setups. Here I'm checking if the part hasn't moved in its setup. Countersinking the backside. Next we machine this hole pattern here. We have 4 holes, 2 of them are tight tolerance holes and 2 of them are through holes for thread and fasteners, and they should be all made in one setup in order to have a precise distance between these 2 tight tolerance holes. Also, this hole pattern should be placed in precise relation to this hole up here. Well, precise, let's say about 1 or 2/10 of a millimeter precise. To locate the hole pattern and top hole, I clamped 2 straight edges as exactly to dimensions as I could onto the blanks and scribed 2 reference lines. For this particular hole pattern I had to use all the X travel that my mill has. So the blank has to be set up just right with the table in its end position to be able to reach all holes, indicating on the back face. Setting 0 on the scribe line. Edge finding for the other coordinates. Center drilling and pre-drilling. Pre-drilling for the reamer. Here I use a reamer which I had to shorten for another job, but it still works fine. Next we have to machine these two M6 holes here, drill and tap them, and then we have to bore out this hole up here to a tight tolerance because this one receives a press fit bushing. Making sure I can reach everything with my Y travel. Indicating along the machine face. This is edge finding for the X coordinates and setting 0 on the scribe line. Here a view of doing the same thing on the other blank. Drilling and tapping the M6 holes. and moving over to the tight tolerance hole location. I used my Wohlhaupter boring head with an extension boring bar and a roughing high-speed insert to dig through the hardened crust. But as you can hear, the blank's pre-cut hole wasn't exactly on center, so I had to start with a heavy eccentrical cut. Checking the cutting edge, but it still looked fine. For finishing, I switched over to a finishing insert with pronounced positive geometry to give a good surface finish. As you can see, I was lazy and didn't bother to grind on the chip breaker onto the insert. But aside from this, it worked very nicely. Then I used the other end of the extension boring bar with its 45-degree holder with a straight cutting insert to chamfer both sides. And finally we have to machine these two heavy chamfers here, which give clearance to another part. These two chamfers are tilted with respect to each other, and the lower one goes fairly deep down into this corner here. Machine setup for this operation is with the vise on the vertical clamping face. Setting up roughly with the level. Setting up thoroughly with the indicator on the machine face. Zeroing the bubble to check later on if the blank has moved in the vise. Tilting the workhead and setting 0 with a ruler held at the reference scribe line. Checking dimension relative to the hole and finishing to dimension. Here I had to use oil for cooling of the roughing end mill because without the table the chips and coolant drop off right down to the shop floor. I didn't want to have a big coolant mess. The end mill held up surprisingly well for both parts. cleaning out the corner where I am forced to climb mill. Here you can see that I couldn't reach everything at the corner. The remainder I milled away with the handheld straight grinder. For machining the second heavy chamfer, I set up with the adjusted level, and the rest was easy peasy. And deburring with the stone. Oh yeah, just feels like baby poop. Here are the finished sidewalls, a view that relieved me very much since no major problems or accidents occurred during machining. I pulled off this job on a 3-day weekend, and afterwards consequently was what the picture suggests. Well, gentlemen, thank you very much for your interest in this video. I appreciate your time. All the best and thank you.